Hello everyone. Today we are going to talk about reaction stoichiometry. From the last episode, we discussed stoichiometry of a chemical compound. This is stoichiometry related to a chemical reaction. Right. The word stoichiometry is from a Greek word stoichion, meaning element, and metron, meaning measure. However, the real meaning of stoichiometry, the chemical meaning, is different. Stoichiometry means chemical quantities participating in a chemical reaction. The chemical reaction can be represented by a balanced chemical equation. So, chemical quantities involving or participating in a chemical reaction which can be represented by a chemical reaction, chemical equation, balanced chemical equation. That is the stoichiometry. Then chemical quantities. How do we measure chemical quantities in our school lab? Okay, we discussed this in the previous section as well. However, we will talk about that again. Right. For example, I am going to take a water sample which contain 1 liter of water at 3.98 degrees Celsius and 1 atm pressure. I have 1 liter of water in my beaker. So these are the different ways of telling the quantity. V, the volume 1 dm cube or 1000 cm cube, centimeter cube, or 1000 milliliters. That is one way of telling chemical quantity. M, the mass. Mass is 1 kilogram because I have used the density of water and I have worked out already if I take 1 decimeter cube of water, what is the mass, and others also I have worked out. Right. So it contains 1 kilogram or 1000 gram. The same quantity can be explained in this method as well. So there is another important method we often use in academic purposes in chemistry, number of moles, simple N. That is actually 55.55. That means if I take 1 liter of water, I have 55.55 moles of water molecules. And capital N, number of particles. There are 3.345 times 10 to the power 23. This time the matter particle in the beaker is nothing but water molecules. There are 3.345 times 10 to the power 23 number of water molecules in this beaker. So these are the 4 basic methods that we express the quantities in the chemical laboratory when we do experiment. Right. However, when it comes to a balanced chemical equation, okay, balanced chemical equation represent a chemical reaction. So this is a combustion reaction of propane. Propane you burn in the kitchen for cooking purpose, for you cook your meals or heat your meals. You use this propane. Propane is one of the major component of household gas, that is LPG, liquefied petroleum gas used in gas cooker. Right. So if you burn it, this is the reaction taking place, which can be represented by the balanced chemical equation. Why a balanced chemical equation must be written, or why the equation must be balanced? Okay, this is the reason. When a chemical reaction take place, number of atoms in the reactant side is exactly equal to the number of atoms in the product side. Atoms are neither destroyed nor created during a chemical reaction. That is nothing but law of conservation of mass. So chemical reaction take place according to the law of conservation of mass, right? So therefore, when you represent a chemical reaction by a balanced chemical equation, it is the correct method. Your equation must be balanced, right? Then there are some important quantitative relationship indicated by this balanced chemical equation. Now we will talk about that. That is actually the stoichiometry, right? What are the information relationship between quantities which involve in a reaction and which is indicated by this balanced chemical equation? All right. So these are the stoichiometric coefficient. Here, the stoichiometric coefficient is 1, 5, stoichiometric coefficient 3, and this is 4. Right. These are stoichiometric coefficients. That stoichiometric coefficient tells you the mole ratio that the chemical quantities or the chemical involving in that reaction. So the mole ratio, 1 mole of propane required 5 moles of oxygen and will produce 3 moles of carbon dioxide, like that. Therefore, the mole ratio you can say 1:5:3:4, like that. Then there is another important way of telling the quantity when it comes to a balanced chemical equation. But even though there are some other methods, this is the most important and this is the easy way to deal with these chemical quantities when it comes to these calculations. Therefore, we stick to these two methods only. Right. What is the other method? The mass ratio. However, we need molar mass to convert number of moles into mass. Okay, 1 mole mean 44 grams of propane. Then 5 moles mean 32 into 5, that is 160 grams of oxygen. On the other hand, carbon dioxide 132 grams and water 72 grams. So mass ratio 44 is to 160 is to 132 is to 72, that is the mass ratio. The meaning is, if I burn 44 grams of propane, I need 160 grams of oxygen for this combustion. The minimum amount of oxygen required is 160 grams. And I can get 132 grams of carbon dioxide. So that is the stoichiometric relationship. Stoichiometric relationship mainly expressed in terms of number of moles. That is the most common. And also, this is also common in terms of mass of chemical involving in a chemical reaction. Right. The next, we can use the stoichiometric relationship for calculations. Okay, this time we are going to use this stoichiometric relationship in a simple chemical calculation. The question is, I have 100 grams of C3H8 propane. What is the mass of carbon dioxide produced? That is the question. Right. We can come to the right relationship. So, mass of propane and mass of carbon dioxide. So this relationship help us to do the calculation. So mass of propane 44 grams will produce 132 grams of carbon dioxide. That is the stoichiometric relationship, mass ratio. So it is easiest to usually when we write ratios, we don't indicate units. But in this method, it is easiest to leave unit with the stoichiometric ratio. Then we are getting the answer with the appropriate unit. So we are going to leave the unit as well. So mass of propane is to mass of carbon dioxide. 44 gram is to 132 grams. So I have 100 grams, not 44 grams. So I need to convert this 44 grams into 100 grams. It is easy me to make 44 uh, or convert 44 into 1. It's easy me to uh, do that and go ahead with the calculation. So I'm going to divide both sides by 44 because any ratio can be divided by the same number both sides. Right? When I divide, I'm getting 1 gram is to 3 grams. Then what I am going to do, I am going to multiply this with 100. Then 100 grams into 300 grams. Both sides of the ratio must be multiplied. Then this is the quantity given to me, that is here. Then this tells us if I use 100 grams of propane, I will get 300 grams of carbon dioxide. So the answer is mass of carbon dioxide is 300 grams. Okay, this time the quantity given is 11,000 grams of propane. How many moles of oxygen required for this combustion? So that is the question. This time the stoichiometric relationship not between two masses, mass and number of moles. So you can see this cross relationship. If I want, if I have 44 grams of propane, 5 moles of oxygen required for that combustion. 5 moles of oxygen. 44 grams, 5 moles. So I am going to write the stoichiometric relationship. Mass of propane is to number of moles of oxygen. It's a cross relationship. Right. Then 44 grams required 5 moles. So I am going to use that the previously I used the method. I divide it by 44 and multiply by 100 1100 grams, 1100. So what I am getting unit, I will leave unit as it is, then 44 cancels, I am getting 1100 grams. That is the quantity given to me. The other side, if I simplify this, I am getting 125 moles. So therefore the answer is number of moles of oxygen required is 125 moles. Now the question is slightly altered. Same quantity as in the previous calculation, 1100 propane is available, and this time they ask how many oxygen molecules, number of particles required for this combustion. That is the question. That's capital N. Right. Okay, I can go ahead with the same calculation. If they ask me to find out number of molecules, I don't straight away find out number of molecules. Actually, I could, but I don't use that method. That's a little bit of confusing. Confusions are there. It's confusing. Therefore, what I'm going to do, find out the number of moles first. Right. Then mass of propane is to number of moles of oxygen. That's again, I'm going to do the workings and find out number of moles of oxygen required, that is 125 moles. Now I can convert that number of moles into number of particles very easily. Number of particles of oxygen molecules, which is going to be 125 moles multiplied by Avogadro number, that is 6.022 times 10 to the power 23 per mole. So you are getting the answer if you simplify this, this is how you easily find out number of particles when the mass is given. Mass of propane is given, number of particles of or number of molecules of oxygen is calculated here. Right, this time the problem, I want 12.044 times 10 to the power 24 number of carbon dioxide molecules. What is the mass of propane must be combusted in order to obtain this number of molecules? So that is the question. All right, before we go to stoichiometric relationship, in this case, if number of molecules is given, I convert it into number of moles. I could use it directly, but that is little confusing. So what I am going to do, I am going to convert that into number of moles. I can use this equation, number of molecules divided by Avogadro number is equal to number of moles. So I am getting 200 moles of carbon dioxide. Then I can go for the stoichiometric relationship. The stoichiometric relationship is this, carbon dioxide 3 moles required 44 grams to be combusted. 3 moles of carbon dioxide to be produced. The required number of propane, so required mass of propane is 44 grams. That is the stoichiometric relationship. So 3 moles required 44 grams. So again, I am going to convert that into 200 in this method, this simplification method, divided by 3, then it becomes 1 and multiply by 2. I had to do that for the both sides. Right. Then 200 mole. 200 mole is the moles of carbon dioxide. Right. Then that is 200 mole equivalents to 12.044 times 10 to the power 25 molecules. So then 200 mole required the mass of propane 2933.33. That is the mass of propane. So that is the answer.